Hi everyone, my name's Adam Feldscher, and I'm going to give you a quick overview of lock and wait-free methods and really sort of what these things are and give you a few quick examples of some implementations. So when we start off just by saying, what is lock-free programming? And a lot of people often think that this means we're not going to use mutex locks, but this really isn't the case because you can use semaphores, you can use monitors, or even like a while loop, like I have down in the right corner there, can be blocking or can be a lock. So really, the formal definition of this is any infinite execution where infinitely often some method call finishes. Now it sounds a little confusing, but really what we're saying is there's always progress being made. So I can suspend any one thread, and no matter what happens, things will always progress. So no one thread will starve out any other thread. No one thread will block any other thread. Um, and there's also wait free, which I'll get to further on, which sort of is a stronger statement than this. And these lock free methods are used a lot in databases because they're sort of systems where we need things to be guaranteed to always proceeding, but we don't need to guarantee that things will happen in constant amounts of time. So atomic operations are very useful in lock-free programming, and we've discussed these a lot in class. But really what an atomic operation is that no one thread can observe any other thread in the middle of an operation. So these are a lot of things like if we have a read, modify, write, the thread can sort of make a call that will read a value, maybe do a compare and swap or something like that, and then write the answer back. And every other thread will pick this up, and no one can interrupt that process. And that's really nothing crazy. It's very straightforward. And any thread, if two threads are trying to execute the same atomic block of code, they'll get executed sequentially. And these are usually a very, very small number of machine instructions, 10 to 15, something like that. So it's really not an issue. So a compare and swap loop is a very common method for lock-free programming. And really what you're doing is you decide you're going to make local changes, and then you're going to compare and swap your changes with the sort of known good global variables to publish them to the other threads. And you're going to assert that nothing changed. So you're going to basically make some sort of assumption, do a bunch of stuff, and then check that that assumption is still true. And if it is, you're good to go. You can publish these changes. And if not, well, someone else changed something, right? So why don't we start over and try this again? So here's actually a nice example. It's C++ code, but it's very, very simple, so it should be fine. So if we see this method here takes, it's a linked list, and it's taking a new node in and pushing it to the front of the list. And so this starts out by taking the shared variable, the old head, and saving it as its local copy right there. And then we're going to go and do some speculative work here, it says. So what we're doing is really we're adding our new element to the front, and now we're pointing its next pointer to the old head. And then we're going to say, okay, now we're done all our work, right? And sometimes this can be a lot more complicated of a section, but in this case, it's pretty simple. And now we're going to go and we're going to publish it. So right here, it's doing a compare swap of the old head. And we're basically checking that the old head value is still what we assumed it was up here. We're going to check that the global head's the same as this head. And then if it is, we're going to go and make a swap. And if it works, great. And if not, we see we have this loop up here. So we're just going to loop back around again and start the whole thing over. So it'll grab the new global head again and start over and then try to add ourselves to the front. The main thing really being that if there's a context switch right in here or right in here, it could mess us up if someone else tries to do a push, but it's fine because we'll start over again. And really what comes in with this being lock-free is that even say we have to loop back around again, you could say, well, this will go on forever. But even if this thread has to loop back around again, it means some other thread did make progress. And that's really where that big difference comes in. So along with this the idea of some thread always makes progress, there's this neat design pattern called the LMAX disruptor. And this isn't really a traditional lock-free programming method, but it's a good example of it. So I thought I would just bring it up real quick. So the idea here being that it's a producer-consumer problem where this receiver here is our producer. So he's going in a ring buffer, which is really just think about this as a big list, but it wraps back around again. You have really just a counter with like a mod or something like that would start back over. And so it's going to keep writing around in this big circle. And he's always writing up ahead, and these guys are always consuming behind him. And now we sort of did something like this in class the other day, except our producer consumer was blocking. So the nice part about this is that these threads here are always advancing. And again, you could block this thread or this thread or this thread, and they're never going to block each other, right? When they catch up to the receiver, they will block, but this actually isn't really considered an issue with lock-free programming because there's no data, right? There's nothing to do. So if there's nothing to do when people are waiting around for data, that's fine. So these guys are going to go and progress up. And so a lot of these things don't need to all be happening at the same time. So some of them, like certain things, this is an assembly line. Maybe this guy's putting the hood on the car, this guy's putting the doors on the car, this guy's doing the interior. And sometimes we do have certain rules. So there's some stuff written over here about what's going on with these exact jobs. So maybe in certain cases you want to assert that the end marshaller doesn't get ahead of the replicator or something like that. Which you could do by just making these counters volatile and then just putting checks against them. But that really wouldn't be too big of a deal and still would keep it lock free. So basically just saying that all these threads can progress and stopping no one thread prevents another thread from progressing. So now let's talk about wait-free methods. So wait-free methods are stronger than lock-free. And so the formal definition here being that every call finishes its execution in a finite number of steps. So really what we're saying is that in some set amount of time, and we'll talk about, there's some stipulations on what defines finite in a second, but in some finite amount of time, this method call will return. And so no computation is ever blocked by any other computation. So really we're saying before with lock free, we had that we could sort of try again as long as somebody else finished, it was fine. Now we're saying no matter what, this computation will always finish. And this really gets more important with really critical things. So like nuclear reactor control code, maybe some operation needs to happen like now. We don't want to be like, well, this other thread came up and he kind of wanted to do it first. Like this thread needs to get its code run right away. So it's really more mission critical things where we need to have these strong guarantees. And they can be proven, right? We could write a proof that something's wait free versus lock free and then go and compare the two. And there's a pretty distinct difference between the code, and I'll show some examples of that. So here's the sort of definition of the number of steps. So we can see we have this hierarchy here where lock-free is the biggest category, with wait-free, we have wait-free bounded and wait-free population oblivious. And the real distinction is lock-free versus wait-free, but these two are sort of interesting just to think about. So wait-free, again, we were talking about just any sort of finite number of steps, right? Wait-free bounded is a bounded number of steps. So maybe you have some sort of a constant figure that you're saying, this one's finite, meaning that we can write a proof that eventually, right, it will finish, and not infinite. Bounded could be there's some sort of consonants below, or even a constant proportional to the number of threads. And then wait-free population oblivious is a constant that's bounded that's not proportional to the number of threads. So this would be a true constant. So maybe you could say, in 10 iterations, it will always be done no matter what, or 10 machine instructions, this method call will always be over. So one good example of a wait-free program is the Java concurrent linked queue. And we will actually be looking a bit more into this later. But here's just the remove method. And so one thing you can see here is that it's going, and so it just does its check that the item's not null, or some basic stuff like that. And then it's walking the list to find the object that it's trying to remove. And then it's going and it says if it's not null and it equals the item we're looking for, right? So we found the item, that it's going to do a compare and swap on the item with null. And so if this works, right, the compare and swap will be successful because it's going to take our item and replace it with null, and then it's going to return true, otherwise it'll return false. And now one important thing, like reading this, right, it sounds simple. But the important thing here, right, is that by deleting an item, they're not actually doing anything with it, right? They're not trying to remanage pointers or something like that because it's a linked list in here. They're just setting it to null and then it gets repaired later. And I'll show you more of really what's going on with these wait-free items. But effectively, as you go through every list operation, there needs to be some sort of clever way to go and work on a situation that this will always work no matter what happened. There can't be that sort of loop and come back around again type thing from the lock-free method. It needs to be just this code will work no matter what. And there's some weird tricks you have to do. So I'll bring up this Java concurrent linked queue. And from what I've read, this actually is one of the sort of best wait-free examples you can find out there. So one thing that comes up, and that's actually a common problem in lock and wait-free methods, is the ABA problem. And so this problem comes about when one thread starts a change, another thread switches in and makes changes, but then switches back. And then our original thread comes back in again and then checks its initial assumption that we talked about. And now suddenly all these things are awry because it thinks that the assumption was still true and it's not. And I have a little illustration to go through and show this to you guys. So if you see here, we start out with this linked list, right? Our head's at the beginning, that's simple enough. And then thread one tries to pop A. So it makes a local head in its sort of little thing, and then it's going to publish its results. But just before that happens, another thread comes along. So thread two comes along and it pops off A, and it did its thing with the local head and all that, but it didn't get constant switched out. It did its compare swap, and now this is our list. The local head from A you can see is still sitting right here from thread one, but we'll see now thread two decides to pop B, right? So now, all right, this is also an issue because now we have our pointer still from the compare swap is down here, which this would be okay, right? Because it would try to compare swap and see head is now different. However, we have B goes and or thread two goes and puts A back. And this is where you can see there's a problem, right? Because we went to our A, right? Our B just happened now where it deleted this node B and then put A back in the front. And now we're going to switch back to thread one and it's going to come back up. And here's what thread one thinks is going on, right? So thread one thinks we have this real list. It thinks it put its local head here, and it's going to go and check and say, oh, is head still at A? Head still at A, good, I can compare swap my head with that. But really what's happening is this picture up here where it's going to try and switch head with local head. And now you can see we're going to put the real head down here at B, which is sort of a thrown out node, right? So now we've lost our list and we have head pointing at this garbage pointer that really isn't useful to us. So it's kind of a dangerous thing to do. And you can see it's not an obvious problem, but you don't think this off the top of your head that you could get this very specific ordering that could mess up your stuff. So there's a few workarounds for it. One is called a tagged state, which actually isn't too great of a solution. It depends on your problem, right? You could probably prove that this would be okay in certain scenarios, but basically you attach a counter to go with your pointers so that say we did all that nonsense where B was going around and making all these switches, right? You would have a counter associated with it. And then you would know that, okay, we moved head back and forth, or we added A back in there, and it wouldn't be, could tell that something else had changed because we have this counter associated with it. So this can wrap around again if your counter's not big enough and things like that. You can store these counters inside the pointer, depending on what kind of pointers you have, and if your compare swap can take two values. So there's some stipulations there. One sort of better solution I found is to use intermediate nodes. So rather than storing A directly, you store a node that contains A. So like in Java, for example, all our items are or all our objects are garbage collected, right? So we always get a new node every time. So the pointers will always be different. So it's really not an issue. So this A here, right, would be a different A, and then it would try to do its compare swap and say, oh, these aren't the same thing. I'm going to try again, loop back around or whatever, however the code's implemented. So that sort of takes care of that problem for us. So now I have some implementation to show you guys, and I might actually do that in a part two because I think my video is about to expire. But thank you for watching the presentation.